Hello, welcome to our project. Firstly, I will introduce the predictive text that guides our project. I will briefly explain the problem we aim to solve, the metrics we use, how we validate the model, and how the features are constructed. These elements together define the foundation for all later modeling work. Our goal is to predict the star rating of Amazon musical instrument reviews using two types of information: the written review text and the selected metadata. The review text provides the customer's actual feedback. The metadata fills at the context about reviewer credibility and how the community responds. Although the rating is between 1 and 5 stars, we treat the problem as a regression task. This allows the model to capture more subtle sentiment differences rather than forcing everything into fixed category. The model output is a continuous prediction, and we evaluate its quality mainly using RMSE, with MAE as a secondary metric. Why RMSE? We choose RMSE because it penalizes large mistakes more strongly. For example, predicting a 5-star rating when the true rating is 1 star is a much more serious error than being off by 1 star. RMSE reflects this difference, making it a more sensitive measurement of model accuracy. MAE complements RMSE by showing the average prediction error in a simple, easy-to-interpret way. To measure performance, we use an 80-20 train test split. The model is trained 80% of the data and tested on the remaining 20%. We also capture the model's performance to simple baseline, such as predicting the average rating. The model is considered meaningful only if it does better than this baseline on both RMSE and MAE. This comparison confirms that the model is capturing real pattern rather than just reflecting dataset tendency. To transform raw text into numerical features, we use TF-IDF vectorization. TF-IDF provides a high-dimensional representation of the review text and highlights important words and phrases. It works efficiently with linear regression models and widely used for large-scale text analysis. We also add metadata, verified purchase, helpful votes, and total votes to the feature set. This structured variables supply additional signals, such as reviewer reliability and community engagement, which can complement the information found in the text. Our exploratory analysis supports this feature design. We observe that longer, more detailed reviews often correspond to higher ratings, while reviews with negative words tend to receive lower ratings. We also find that metadata plays a meaningful role. Verified purchasers generally give more valuable feedback, and the reviews with many helpful votes often reflect stronger sentiment. This pattern confirms that TF-IDF text features combined with the selected metadata from a solid base for rating predicts.
I'm going to talk about part 2, exploratory data analyzed and pre-processing. The number 1 is data overview. The raw dataset have 900 key reviews. We select useful column and clear missing value. Keep a sample of 100 key for efficient dialing. This is total dataset. And the next is select useful column and the head and find a model and 100 key rules. Now the plot is begin. 2.1 Star rating distribution. Star rating distribution plot, we can see that most rating are 5 stars. Data is highly imbalanced, which is typical for Amazon. The next is 2.2 Review test length. This plot is very interesting. It shows the most reviews are between 100 to 500 kilometers. We can see there. No, I'm sorry, 100 to 500 characters. Yeah. We kept the distribution at 2000 characters for clear visualization. Yeah, I kept it because I want to make the plot more beautiful. The 2.3 is helpful words analyzed. Helpful words are extremely skewed. Most review has 0 or 1 words. Low star reviews tend to reviews slightly more helpful words. Yeah, this plot can show that. The low star reviews the more helpful words. Example 1 stars or 2 stars, right? The 1 stars has more. 2.4 Review active over time. Review volume increased sharply after 2010, peaking around 2014 to 2015. This shows the data site is mostly recent reviews. 2.6 is product statics. Most products has only 1 to 5 reviews, while a few popular instruments receive many reviews. The long-tailed pattern is typical for Amazon data.
In this section, I will provide an overview of the modeling framework used to predict the star ratings from Amazon Musical instrument reviews. I will focus on the reasoning behind our model choices, the structure of our feature representations, and the several critical considerations that influence the implementation. To model the numerical star ratings, we rely on linear regression techniques applied to TF-IDF-based text features. This family of models offers a strong balance between interpretability, computational efficiency, and predictive performance. Linear regression serves as a natural starting point because it directly captures global relationship between electrical patterns and rating outcomes. However, given the high dimensionality of TF-IDF features, the basic linear model tends to overfit. To address this challenge, we incorporated the ridge regression, which extends the linear model by applying a L2 regularization penalty. This construct stabilizes the coefficient magnitudes and helps reduce variance, making ridge considerably more robust in sparse and noise-tax environments. As a result, ridge regression represents an efficient and scalable approach for this predict text. Our modeling approach relies primarily on TF-IDF representations derived from unigrams and bigrams. This transformation captures the importance of individual tokens and short phrases, while furthering the sparsity needed for efficient linear modeling. In addition to the text features, we enrich the representation by appending methods such as verified purchase, helpful votes, and the total votes. These variables contribute meaningful contextual information about reviewer credibility and community engagement, and they complement the sentiment signals extracted from the review text. The implementation begins with loading the dataset, remove entires with missing or malformed reviews, and applying TF-IDF vectorization with maximum vocabulary size of 50,000 terms. The metadata fields are normalized and concatenated with the TF-IDF matrix to form the complete input for model training. Both linear regression and ridge regression models are then trained on this combined feature set and evaluated on an independent 20% test split. The results show a clear contrast between the two models. TF-IDF with a linear regression products an RMSE of 1.2 and a MAE of 0.76, while TF-IDF with a ridge regression improved performance significantly, achieving a RMSE of 0.75 and a MAE of 0.50. This result validates the importance of regularization in managing variance and enhance generalization. Our evaluation relies on an 80-20 trend test split, with RMSE serving as the primary metric because it pencilizes large deviations more thoroughly, a crucial consideration when predicting user ratings. MAE is reported as a secondary measure that summarizes the average prediction error. This evaluation structure ensures that the models are tested against unseen data and that their performance can be meaningfully compared to simple baseline predictors. The high dimensionality of TF-IDF features introduce important computational challenges. To ensure the workflow remains efficient, we cap the feature size, apply minimum document frequencies thresholds, and rely on sparse matrix representations throughout the pipeline. These steps reduce memory load and allow the models to be trained efficiently on a larger subset of review data. To maintain data quality, we excluded rows with missing review text or missing rating. The metadata variables, particularly helpful votes and total votes, exhibit heavy skew, but the ridge regression remains robust in the presence of the noise due to its regularization. The verified purchases indicate as a reliable, low variance signal that reinforces the text-based sentiment patterns without introducing instability.
Part 4 Evaluation. The 4.1 baseline evaluation. We start with two simple baseline methods, global mean rating and per product mean rating. This is the data set and the result of the data set. Number one, global mean rating. This model always predicts the average rating of all reviews. And number two, per product mean rating. This model predicts the average rating for each product based on past reviews. Both baseline get RMSE of about 1.25. Yeah. And they capture basic patterns like the fact that Amazon reviews are usually positive, but they can't understand the review text or any detailed differences between reviews. And 2.4, we use the TF-IDF model evaluation. The next, we test two models that use TF-IDF to turn the review text into numerical features. We also add metadata when available. First one, TF-IDI plus linear. This model improves the RMSE about 1.2, showing that using text makes prediction much better than simple average. The number two model is TF-IDI plus Ridge, and this is the best model. It reaches RMSE about 0.75 and MAE approximately 0.51. This is a big improvement. Shows that two things. The review test is very helpful. The word people use clearly relate to the ratings they give. Second, Ridge work well with TF-IDF because it prevents overfitting when the number of test feature is very large. Overall, TF-IDI plus Ridge is a strong, fast, and reasonable model for predicting ratings from Amazon review data. That's all. Thank you.
Last part about related work, the musical instrument subset used in this project is diverse from the Amazon Review Corps released by our professor and their team at UCSD. The benchmark widely used for large-scale sentiment analysis, recommendation modeling, and user behavior research. Similarly, rating prediction texts have been explored on other public datasets such as Yelp and IMDb, establishing text-based regression as a well-studied problem across the domains. The lecture generally distinguishes between traditional TF-IDF-based linear models and instead of the deep learning approaches, such as BERT. Traditional models, particularly TF-IDF paired with ridge regression, remains competitive on large sparse dataset due to their efficiency and interpretability, while deep learning models achieve stronger accuracy and higher computational cost. Our findings aligned with this established perspective. The TF-IDF ridge pipeline outperforms simply baseline on our dataset, confirming the effectiveness of traditional feature-based methods for scalable rating prediction.